Welcome. Today we're going to be working with simplest radical form. So we have been seeing radicals like square roots or even sometimes cube roots in the past. And when we're taking the square root of a perfect square, we come out with a nice integer answer. If you try to take the square root of something that's not a perfect square, for instance, the square root of 45, if you put that into your calculator, you're going to get a decimal answer. Unfortunately, that decimal answer is going to cause us some rounding errors. So we're going to rewrite this in what's called simplest radical form. It makes our calculations easier and it avoids the rounding errors. So the process for doing this is going to involve making a factor tree. So we're talking about thinking about two numbers you can multiply together to make 45. It could be any pair of numbers. So maybe you're going to go with a 3 times a 15, or maybe you're going to go with a 5 times a 9, whatever you choose. And as you're making this factor tree, your goal is to break down each number into the primes. So 3 is a prime. I'm going to circle that so I keep it in mind. 15 is not a prime. I can still break that apart into two more factors. 15 I get when I do a 3 times a 5. 3 is a prime, we know. Oh, and 5 is also a prime. So now that I have every prime number possible from this, look at those. I'm going to focus on the index of my radical. Now, in example 2, it's a little bit easier to see. The index is this 3 that sits on the shelf as a cube root. In example 1, there is no number sitting on the shelf there. It's a square root. Anytime that you have a square root, it is understood to be an invisible 2. So I need to find matches in groups of 2 in that factor tree. So anytime that I can find a number that matches, I'm going to write it down once. Numbers without a match, just looking at those primes again, I'm not worried about the 15 because I've already taken care of it lower, but just looking at those numbers and that were prime without a match, that's going to stay inside of the radical. So this is my simplest radical form. You can go ahead and check this. You can type the square root of 45 into your calculator, and then you can also type 3 times the square root of 5 into your calculator. Both of those will give you the same decimal value. They're equivalent, but this 3 times the square root of 5 makes it easier for us to do other calculations. So let's continue on then, and we will work with that example number 2. We've got the cube root of 320. So for that, I've got to start thinking, what numbers can we divide to get 320? So I see it ends in a 0, so I know that it's got to be able to divide by 10. So we could do 10 times 32. 10 is not a prime, so I'm going to keep on going. That's going to be a 5 times a 2. 5 is prime, so I can circle it. 2 is prime, so I can circle it. So now what numbers can I multiply together to make a 32? Well, you see it's even. Maybe you want to do 2 in something. Perhaps you recognize that 32 is 4 times 8. That is fine as well, however you want to work with that. So I'm going to go with 2 times 16, and 2 is a prime. 16 could be 2 times 8, where 2 is a prime. 8 is 2 times 4 for us, and 2 is a prime. 4 is not yet prime. I can keep going. 2 times 2. So depending upon what pairs of numbers, which factors you used, your factor tree may be a little bit more symmetrical, or it may run down one side more. That's okay in any case. No matter what two pairs you use, as long as they do multiply to give you that number that was up above it, you're going to end up with the same amount and same types of those prime numbers that we have at the bottoms. So now that we've got all the prime numbers, we are looking at the index. My index here is a 3, so I need to find numbers that repeat in matches of 3s. So I've got the number 2 that shows up 3 times. Every time I find a group of 2s, I'm going to write it down once. And every time I find another group of 2s, it shows up 3 times there, I'm going to write it down once outside. Remember, all of these values in the factor tree were multiplied, so I'm still going to be thinking about multiplication with these. Anything that was not with a match is going to stay at home inside the radical. It's still that cube root, so it still has to have that 3 index, and it's my poor number 5 that's the prime without a match. So I just have to clean this up. Numbers that are outside of the radical, if I end up with multiple numbers there, we multiply them, get a 4. And if it would be necessary, any numbers under the radical could also multiply if I had more than one left. So 4 times the cube root of 5 is the same as the cube root of 320. Again, you could type both of those into your Desmos calculator and compare their decimals to confirm that you got that correct. Example 3, we're going to go ahead again and try this out. Think about numbers that you can multiply together to get 240. And again, I see that that ends in a 0, so I'm going to focus on saying that it can be divided by 10. So that would be a 10 times a 24. And I know 10 is 5 times 2. 5's a prime and 2's a prime. I circle those to really draw my attention to them. 24 is a composite number. 24 I could treat as a 4 times a 6. 4 I know has factors of 2 times 2, so I found some primes. 6 has factors of 2 times 3, so we found those. Now, think about your index. What number is sitting on the shelf? That is a square root, so this is an invisible 2. So I just need to have 2 matches to make a group. So let's see, a match of 2's, and I can write that down once. A match of 2's here, we can write that down once. I've got a number 5 that's a prime. It doesn't have any other 5's to match up with, so that's going to stay inside of our radical. I also see that I have a 3 in my prime listing. I don't have any other 3's in my primes. That also has to be inside the radical. And as I mentioned, remember that everything in the factor tree is multiplying. So values outside of the radical multiply together. 2 times 2 is 4. Values inside the radical multiply together. 5 times 3 is 15. So we're talking about 4 times the square root of 15 being equivalent to the square root of 240. Let's go with another example here. I hope you're starting to see the pattern here and catching on a little bit. So I'm thinking about 24. What are some factors of 24 that I can use? Maybe I'm going to choose 8 times 3. I know 3 is a prime number. 8 is not a prime number. I know that that's 2 times 4. 2 is at least a prime, so I'm working my way there. And 4 is not prime. No way, dude. That's going to be a 2 times a 2. So I'm thinking about a cube root. Got to look for groups of 3. I need the same number 3 times to be a match, to be a group. So there it is. Every time I find that group, I write the number once. And any values that do not have a match stay inside of the radical. And don't forget your index. It was a cube root, so you got to indicate that cube root to us so that we understand the value outside had occurred 3 times over in the factor tree. 2 times the cube root of 3 is the same as the cube root of 24. Next up, we've got 144. That's not a prime number. 144 there is happens to be a perfect square. It's a 12 times a 12. But I can't do anything with it because I'm not talking about the square root of 144. I'm talking about the 4th root of 144. So I still have to make that factor tree and break this apart. Think about what makes a 12. Maybe I'm going to go with a 3 times a 4, and 3 is prime. 4 is composite, so I've got to break that into a 2 times 2. I mean, maybe I want to be a little different on this side of the branches. Maybe I'm going to go with a 2 times a 6, and 6 happens to be a 2 times a 3. So see what you got there for your primes. Now you're going for a 4th root. This means that the number has to appear 4 times over in order to make a group and pull outside of that radical symbol. So I've got the number 2 that shows up. It's duplicated over 4 times, so that number gets written once outside the radical. And my radical is the entire 4th root with that index symbol. Now I do have a 3 and a 3, and while those 3's are matches, they cannot come outside because they're not matches of 4 times over. They are only twins. We would need quadruplets here with an index of 4. So that 3 that's left over is going to stay under the radical, and also this 3 that wasn't used with a match stays under the radical. So you get to simplify. 2 times the 4th root of 9 is what we're looking at. That's the equivalent of the 4th root of 144. Take a moment and try that number 6 on your own. Pause the video, work it out, and then once you think you have your answer, press play again. Let's see if you got it right. Okay, well, welcome back. Let's see how this goes. So 525, what is it that you can divide that by? Well, if it ends in a 25, I've got to be able to divide it by 25. So maybe I'm going to choose 25 times 21. You could have certainly also gone with the fact that 525 could be divided by 5. Maybe you do 5 and 105. That's fine as well. But that's not prime. I got to keep going. 25 is a 5 times a 5. 21 can be written as a 3 times a 7. And so it's a square root. Now, again, if you chose different factors to start with, that's fine. At your bottoms, you should still have a 3, a 5, and a 7. 4 prime numbers are going to be in that. No matter what shape your tree is, you'll still have 4 prime numbers. With that square root, I want a number that shows up twice, and I get to write the group down once. Anything that doesn't have a match to show up twice is going to stay inside the radical, just like the 3. Anything without a match is going to stay inside the radical. That's my 7. So 5 times the square root of 21 is the same as the square root of 525. I hope that you're grasping onto this and feeling a lot more confident now with how to simplify those radicals.